I'm Victoria Neller,
I'm JT Siebold.
I'm Jude Chiruta.
and our project is on the quotient topology.
Perfect.
I'm gonna have a couple of definitions or several definitions mapped out. So first we have the quotient map. So the quotient map basically, as is described in the textbook, we have, let's say that x and let's say x and y are topological spaces. And we'll have a surjective map. Surjective map will have H. So H going from X to Y. And we say that this is a quotient map. This map is a quotient map when the set U is a subset of Y, which is open in Y, and is open in Y. If and only if H inverse of U is open in X. Now, there is another way to describe this in different terms, and we can describe quotient maps using saturated sets. Basically, we'll say that to describe quotient maps, we'll have in saturated sets, let's say that we have C a subset of X is saturated if set C contains every set of H inverse of Y that it intersects. Thus, we'll say that C is saturated if it equals the complete inverse image of a subset of Y. Alright, and see that the map H would be a quotient map is the same as, once we have determined all this, then we can say that we're basically saying that H is a quotient map is the same as saying H is continuous, which is the same as saying H maps saturated open sets of X to open sets of Y. So essentially what I'm trying to say is H is a quotient map, because remember saturated sets is basically another way of describing quotient maps, just in different terms. So H is a quotient map H is continuous H maps saturated open sets of X to open sets Y. And we'll get into this later, but you can also have saturated closed sets as well. So you can have H maps saturated closed sets of X to closed sets of Y. Yeah. Any questions?
Are there any special cases of quotient maps?
Of course. Let me get that to you soon. So there are different quotient maps. There are two of them. We have open and closed. So let me rewrite this. Keep the definition up here. So two types of quotient maps. We have open and closed. Now, with open maps, basically, we've got to remember that take your map H going from X to Y. Actually, before I even open, actually, you know, use a different marker just to make it easier to organize. Open maps. So, open maps. To lay this out, we have our map H going from X to Y. Now to fit the criteria of open map, this will be open for each open set T of X. And then we'll have the set H of T, which would be open in Y. So I guess a little quick picture. We'll have this space X. Let's have this one Y. Basically, you have your open set T, which is in X. You have your set H of T. Basically, just shape the same. This is just basically a visualization of an open map. All right. Get this out of the way. And then we move on to our closed map. Now, this is pretty much, if you know what open maps is, then you basically already have closed maps. Basically, it's kind of the same definition, just the opposite. So, you would have your map H x to y, closed, and basically, if you remember your open map, it's basically, just to sum it up, it takes closed subsets to closed sets. Yeah, that's basically closed maps. Yeah, you can read it.
Alright, so now we're going to look at the definition of what quotient topology actually is. So we're going to let X be a topological space. And we're also going to have Y as a set. And then we're going to have Q be a function from X to Y. And this is going to be a surjective function. So when we have these three conditions satisfied, then there exists exactly one topology on Y relative to which Q is a quotient map. Then this is going to be the quotient topology induced by Q. So to write this out, then there exists exactly one topology T on Y relative to which Q is a quotient map. So then we have, this is the definition of the quotient topology. Induced by Q. So then we can define the quotient topology with some formulas. So we can have that U subset of Y is open if and only if Q inverse of U is open in X. And then we'll get these following equations, which are going to be really important when it comes to actually showing what a quotient topology is. So we have P inverse of the union over all alpha and j of U of A, U of alpha, equals the union of alpha element of j, P inverse U alpha. Then we're also going to get P inverse of the intersection of I going from 1 to n of U of I, which is equivalent to the intersection of n of I going from 1 to n of P inverse of U of I. So these are going to be some important equations to remember for later on. And so to recap, we have that the quotient topology induced by Q occurs when X is a topological space, Y is a set, Q is a surjective function from X to Y. Then we have that there exists exactly one T on Y relative to which Q is a quotient map. And then we said that when U is a subset of Y is open, this occurs if and only if Q inverse of U is open in X. So this is a lot of words and a lot of letters. So let's try and imagine this in a picture. So let's take this to be X and this to be Y. And then Q is our surjective function going from X to Y. So, we'll take something in X, and we'll call this Q inverse of U. And then in Y, that'll be U. And then take another one. We'll say this is Q inverse of S. And then we'll call this S. And now we see Q is a continuous map from X to Y with T as the quotient topology. So, keeping all of this in mind, now a fun fact that we have is that the quotient topology is actually the largest topology you can put on Y such that the map Q is continuous. So, in order to prove that, we're going to do a proof by contradiction to prove that fun fact we just found through the definition of the quotient topology. So, as a reminder, the fun fact is that the quotient topology is the largest topology you can put on Y such that map Q is continuous. All right, and now to prove this, so we're going to do this through a proof by contradiction. So, by contradiction, we're going to let S be a larger topology on Y. And then we're going to have Y that is not contained in the quotient topology. So since S is not contained in the quotient topology, then we have that Q inverse of S, keeping in mind that Q is our function from X to Y, is not open in X. So now we have a set S in X that is not open. So, since set S of X is not open, then we have that Q is not a continuous map. However, we know that Q actually is a continuous map. So this gives us our contradiction that we are seeking. So, we have Q, not a continuous map. And this gives us our contradiction. Thus, we have proven that the quotient topology is actually the largest topology that you can put on Y such that the map Q from X to Y is actually continuous.
How do we know that the quotient topology is an actual topology?
That's a great question. So, in order to show that the quotient topology is an actual topology, we're going to need to recall the conditions that we need in order to be a topology that we've learned earlier in the course. So, let's recall. In order to be a topology, that we need we need to have the entire set Y and the empty set open. We need them to be closed under arbitrary unions. And 3, we need them to be closed under finite intersections. So these are the 3 things that we're going to need to show in order to demonstrate that the quotient topology is in fact an actual topology. So let's start with 1. So for 1, we're going to just apply the definition that we showed earlier of the quotient topology. So we'll say Q, our function from X to Y. So the inverse of Q of Y equals X. And we know that Q inverse of the empty set is just going to be the empty set itself. And we know that X and the empty set are open in X because the topology on X that we've already established already satisfies these 2 conditions here. So we have just shown that the quotient topology satisfies this first condition. So now for the second condition, to show that it's closed under arbitrary unions. So for this one, we're going to let U sub I be a subset of Y such that U sub I is open. Now, what we want to show is that the union of U sub I, of all U sub I, is going to be open. So to do that, we're again just going to apply the definition of quotient topology, and we're going to get that Q inverse of the union of U sub I is going to equal the union of Q inverse of U sub I. And all of these unions are going to be over I. So, since Q inverse of U sub I is open, the union of the open sets is going to be open just by our very definition that we've discussed earlier in the class, that the union of open sets is going to be an open set. So we have this being open and this being open, so the union of open sets is going to be open on X. So and X satisfies this condition already. So we have shown that the quotient topology satisfies condition 2. Now for condition 3, we want to show that it's closed under finite intersections. So the proof of this is going to be very similar to how we showed that it was closed under arbitrary unions. We're just going to replace all of the union symbols with intersection symbols and assume now we need to assume that we have finitely many UIs. And then we're going to apply the same argument and thus get the result. So what that's going to look like is we're going to let u sub I subset of y be open such that u sub I is finite. And then we're going to say Q inverse of the intersection of I equals 1 to n of u sub I is going to equal the intersection from I equals 1 to n of Q inverse of u sub I. And then we'll apply the same argument as we did above, since Q inverse of this is open, we know the intersection of finitely many sets is going to be open on X again, and so we have shown that then we know that X is also satisfies this, so we have shown that the quotient topology satisfies the third condition of what it means to be a topology. And then, if we want to think about an easy way to think about topology, can you stop it?
So what's an easy way to think about the quotient topology?
That's a great question. So let's first start off with what it means to be a surjective function, since our function q from x to y is assumed to be surjective. So, as we know, surjective function, let's draw a picture of what it means to be a surjective function. So this is our q, and we're going from x to y. We're going to take this part of x, and it's going to map to a single point in y. And then we call q inverse of this singleton set of y, when this is point y, is going to be a fiber over y. Then we can find all fibers for all points in y, then these fibers subdivide x, and then these fibers are also mutually disjoint. So what that would look like is us taking a partition of x indexed by y. So what that would look like is, again, let's draw x and y. So this is going to be x going to y. And let's subdivide x and y. So we'll have the blue portion going to our blue point. A green portion going to a green point. And we'll have a red portion going to our red point over there. Then, here we are expressing x as a disjoint union of non-empty sets such that their union is x. So, disjoint union, blue and green and red, none of them they don't intersect at all, and their union makes up all of x. So this partition image allows us to think about y as a collapsed version of x by q. So since we have this as our function q, actually what we're seeing here is x is being collapsed down. These sets are being collapsed down into single points here, since we have this entire set of values of blue going to a single point, our entire set of values of green going to a single point, and our entire set of values of red, again, going to a single point. So, x is being collapsed down to y, which is the very basic idea of what it means to be a quotient topology, and what we've seen as quotient maps, and turning a turning a circle into a sphere. So, now let's think about an example. So, example, let P be the map of R onto the 3-point set A. Which consists of A, B, and C, defined by P of X, A, B, and C. A is when X is greater than 0, B is when X is less than 0, and C is when X is equivalent to 0. So, then if we want to think about this as an actual picture, an image, a graph, we have this big circle, and we're going to put C in this circle. And then we're going to have another one, and in this is going to contain another one, and we're going to put point A inside this really small one, and we're going to put point B in another small one. So this is what the image of this quotient topology induced by P is going to look like. And so hence the quotient topology on A must be T. This is going to be our quotient topology on A. It's going to consist of, obviously we're going to have the empty set in there. And we're going to have the entire set in there as well. So we're going to have A, B, and C. But then we're also going to have A by itself as a singleton, B by itself as a singleton, and A and B together. And so this is going to be the quotient topology on A.
Yeah.
All right, there you go.
Okay, so now we're going to talk about what a quotient space is. When we're talking about a quotient space, we should probably first define it. So the definition goes as follows. We let X be a topological space. And we let X star be the partition of X. We let it be the partition of X into disjoint subsets whose union is X. Okay, from here, you want to have a projection map P. So let us have a projection map P. Map P, where we can define P as being what takes us from X to the partition of X. So from here, we want to let P be a surjective map. Let P be a surjective map that carries each point from X to the elements partition of x. Since p goes from x to partition of x, we want p to go from a point in x, should be two different words, to the partition of x. So then this induces the quotient topology. Yes, this induces quotient topology. And then the space for our partition of x is what we call the quotient space of x. And then just some other notes. There's an equivalence relation in x such that all elements of our partition of x are actually equivalence classes. So that's the relation, and this would be the class. And then people don't always call the quotient space the quotient space. It also has other names. So since the partition of x is being obtained by identifying equivalent pairs, equivalent points, so sometimes you'll hear the partition of x be called the identification or decomposition space instead of the quotient space. And then we can kind of think about this as the very first thing we're trying to be into, kind of like the gluing where we can shape things. So I don't remember, like Professor first said you can rearrange a coffee mug into a donut by like re-molding it and such. So we can kind of think of this as the concept of gluing as well. So let me erase this one. So if we let ourselves have a circle called x, we're going to define x as, should we draw the circle first? So we can define this circle as x cross y, where x squared plus y squared is less than or equal to 1. We have this one to shape this in. So here we have our circle, which is just x squared plus y squared across y. Then we have this little shaded circle and this big shaded circle. What we can think about those are the saturated regions that are open in x, where this whole circle is our x. Since before we define the quotient space as the projection map from x to the partition of x. So we can actually do something very similar here where we have this as x. And we can use our projection map P to get to partition of x. With this we can actually turn into a sphere. You can imagine this is a sphere. My drawing isn't the best. Where we had our shaded regions, our saturated regions U and V, that started off as flat points, this a smaller circle, and this being a larger circle that kind of encapsulates the outside edge of x. We have this go to this. So we have a little point, imagine this is shaded, a point U, which originated from this and got carried over by P, so we have P of U. Then very similar, we have V, where we had V right here. After the projection map P, we have P of V, which is a point here. Oh, and then we can also define the sphere as just the basic sphere where we have x squared plus y squared plus z squared equals 1, which kind of defines what this is. then what we just showed here is actually an example of the unit 2 sphere, which is a very good way to kind of visualize what's going on with the quotient space. Yeah. And then from this too, we can also see that, or from this, we can also learn that the partition of X is also homeomorphic with R cubed, since this is inside R cubed. And that's all I got. Okay, you're good.
Alright, so now let's discuss some results from our quotient map. So the first result we're gonna see is that the composition of quotient maps actually behaves very nicely. This means that the composite map of two quotient maps is also going to be a quotient map. So what that would look like is let P and Q be our quotient maps. Then we have P inverse and pre-image of U. Then Q composed with P is also going to be a quotient map. However, when it comes to the products of quotient maps, this does not behave nicely unless we have extra restrictions placed on the quotient maps that we're using. So what that means is the product of quotient maps is not always necessarily a quotient map itself. So in order for that to hold, the spaces must have local compactness. So for products of maps, in addition to being a quotient map, those maps must also have local compactness. So local compactness is actually something that you'll study later on in the chapter, but not something that we're going to currently be going over today. So, second, we're going to go over that products of maps, in order to be a quotient map, in addition to the local compactness, the spaces must also have that both maps, P and Q, must also be open maps. So P and Q open. So once we have these two conditions satisfied, then we can easily see that P cross Q is an open map. And the result is that the product of P and Q is going to be a quotient map. And then we can also see that if we have an injective quotient map, then this injective quotient map is going to be a homeomorphism. And then finally, we're going to see that the Hausdorff condition doesn't actually behave well under quotient maps. So, for Hausdorff, the additional restriction that we need in order for the Hausdorff condition to hold under quotient maps is that in order for this to hold, each element of the partition of X must be a closed subset of X. So, if we have X, which is we have our quotient map Q going from X to Y, and we have that X is Hausdorff, then each element of partition X prime must be a closed subset of X. And then if that condition holds, then the quotient map also satisfies the Hausdorff condition. And then the most important result that we'll get when studying quotient spaces is actually when we attempt to construct a continuous function on a quotient space, which will lead us into theorem 22.2.
Okay.
So now we're going to look at theorem 22.1, which states that if we let P from X to Y be a quotient map let A be the subspace of X that's saturated with respect to P, and if Q from A to P of A is the map obtained by restricting P, then we get these two properties that follow. So if A is open or closed in X, then Q is going to be a quotient map. And then if P is an open or closed map, then Q is also going to be a quotient map. So before we dive right into the proof, let's just get a visualization of what this is actually meaning. So from here, we have two spaces, X and Y. So this is going to be X. We're going to let this be Y. And then from X to Y, we have P, which is our quotient map. And then inside of X, we have these sets that go 2 points in Y. So we're going to have a blue one, we'll have a green one, and we'll have a red one. And so the blue here gets mapped to the blue and Y, the green and X gets mapped to the green and Y, and the red and X gets mapped to the red and Y. And so that is the visualization of our quotient map P from X to Y. And then if we let A be a subspace of X that's saturated with respect to P. So by our definition of saturated, let's set A as a subspace of X. It's just going to be all of these parts in X, which is going to map to P of A by our equation Q, by our function Q, which is going to be all of these points in Y. And then, so we're going to label this A, and this is going to be P of A. And then we're going to have our function Q, mapping A to P of A. And then, when we're going to prove this theorem, we're going to actually want to prove the idea that Q inverse of V equals P inverse of V when we have V as a subset of P of A and U is a subset of X. So a visualization of this is going to end up being, suppose we take the green and the blue in X and the green and the blue in Y, and we're going to make those P inverse of V and V respectively. So I'll draw it down here. Down here is going to be P inverse of V, and down here is going to be V. And it's going to look like, we're going to have the blue set in here, the blue point in V, and we're going to have the green here, and the green in V. So that is going to help us visualize this and this portion of the theorem. So now we're going to go into the proof of the theorem. You can stop it.
So now to prove theorem 22.1 after our visual. To prove this, we're going to want to verify two things. First, we're going to want to verify what we'll label as I. I want to verify that Q inverse of V is equal to P inverse of V when V is a subset of P of A. And we're also going to want to verify that P of U intersecting with A equals P of U intersecting P of A when U is a subset of X. So first, we're going to check the first one, the first equation. So note that since V is a subset of P of A, and A is saturated, P inverse of V is contained in A. Then what follows is that P inverse of V and Q inverse of V are equal at all points. At all points of A that are mapped P into V. Now we're going to check the second equation. So first note that for any two subsets, U and A of X, we have the following inclusion. P U intersect of A is a subset of P of U intersect of P of A, which is the first inclusion that we're wanting to find. Now to prove the reverse inclusion, we're going to suppose that Y is equal to P of little u, which is equal to P of little a. For little u, an element in big U, and A, element of big A. Since A is saturated, A contains set P inverse of P of little a. So, in particular, A contains U. Then we can see that Y equals P of little u, where little u is an element of U intersect A, which then proves our second equation there. Now, we're going to suppose A is open or P is open. So given our subset V of P of A, we're going to assume Q inverse of V is open in A. So we're going to want to show that V is open in P of A. So suppose that A is open. Since Q inverse of V is open, in A, and A is open in X, we're we're going to set Q inverse of V to be open in X. So, since Q inverse of V is equal to P inverse of V, the latter set is open in X. So that V is open in Y. Because P is a quotient map. So, since Q inverse of V is equal to P inverse of V, and we have Q inverse of V is open in A, we have that P inverse of V is equal to U intersect A. For some set U, which is open in X. Now, we have that P of P inverse of V is equal to V because P is surjective. And P is surjective just by the definition of being a quotient map. Then we have V equal to P of P inverse of V, which is equal to P of U intersect A, which is equal to P of U intersect P of A. Thus, P of U is open in Y. Since P is an open map, hence, V is open in P of A. And so this proof proves only for if A or P are open in X, or this only holds true for if A is open in X or if P is open in an open map. To check for when A is closed in X or when P is a closed map, you would simply do the same thing except replace the words open with closed. But you would use the exact same argument that we have shown here. And thus, so we can say, similarly, if A is closed in X, Q is a quotient map. And if P is a closed map, Q is a quotient map. Thus, we have proved theorem 22.1.
Oh, is it recording?
Yeah.
All right, cool. So this is theorem 22.2. Basically, as it states here, we're going to allow map P to go from X to Y, as you can see. X to Y, this is the map, X to Y, be a quotient map, and let Z be a space. So we added Z as a space, and map G, go from X to Z. That's constant on each set P on each set P inverse of y for elements y that belong to set y. Then we have G inducing a map F from y to z such that F composite P equals G. The induced map F is continuous if and only if G is continuous, and F is a quotient map if and only if G is a quotient map. So that's basically 22.2. And again, this is just a visualization of like what theorem 22.2 looks like. So as stated in the theorem, so we'll have the map P going from X to Y, map G going from X to Z, and then we have our map F going from Y to Z, and we're trying to have making sure that F is continuous if and only if G is continuous. And if you have F being a quotient map, then you'll have G also becoming a quotient map as well. So now we're going to go ahead and go along with the theorem 22.2 proof. So for each y, it's for each element y that belongs to set y, we have G of P inverse of y, which is a 1-point set in Z. Now, if f of y denotes this point, then we have defined the map from F, the map F, which goes from Y to Z. Such that for each element X that belongs to set X. All right, so now we'll have the map F of P of X equal G of X. Now, if F is continuous, then G equals F composite P is also continuous. Now, we take the converse statement, so let's say G is continuous. Now, we're given that there's an open set of Z. Open set V of Z, yes. That means we have G inverse of V is open in set X. But, however, G inverse of V equals P inverse of F inverse of V. Now, because P is a quotient map, then we must, then we know that F inverse of V is open in Y. We come together and we see that F is continuous. Now, we want to go ahead and look at what if F is a quotient map, then G is the composite of two quotient maps right? The two quotient maps being F and P. And thus, this will also make G a quotient map. Now we take the converse statement of that we talked about. So conversely, let's just say that G is a quotient map. Now, since G is surjective, so is F. All right, so G, the map G and the map of F, they're both surjective. So we'll let V be a subset of Z. Okay. Sorry, I have to erase that. Let V be a subset of Z. We must show that V is open in Z if F inverse of V is open in Y. Now, looking at the set, the set P inverse of F inverse of V is open in X because P is continuous. Since this set equals G inverse of V, right? That means the latter is open in X. All right, so that means G inverse of V is open in X. Now, because G is a quotient map, V is open in Z. So throughout the proof, if you noticed, I used the open quotient map definition. As you can see here in this paragraph, and also here as well. Because if we look back to the definition of quotient maps, or at least the characteristics of it, two ways. There are two types of quotient maps, it's open and closed. And we were able to use the open quotient map definition to, that's pretty much like the base of our proof, pretty much. So, yeah.
All right, go ahead.
Good, cool. Okay, so here we have corollary 22.3. Corollary 22.3 basically says that we let G from X to Z be a surjective continuous map. We let the partition of X be the following collection of subsets of X. We have the partition of X equals the set of G inverse of the set Z for all Z and Z. And if we're given the partition of X, the quotient topology has these two things. That's part A. The map induces a bijection continuous map from X from the partition of X, or F, sorry, from the partition of X to Z, which is a homeomorphism, which holds true if and only if G is also a quotient map. And we also have part B, which says that if Z is Hausdorff, so is the partition of X. And to help visualize part A a little bit, I have this little triangle that we draw. So basically we have X goes to Z, and the function G up here. And we can also have X goes to partition of X, which is from the definition of quotient space where we had a projection map that brings X to partition of X. And then from F, which is right here, we have partition of X goes to Z. So it's just like another easier way to kind of visualize what's going on inside this corollary. But yeah, that's corollary 22.3.
Whenever you're ready.
And then for the proof of 22.3, for part A, we first have by 22.3, by 22.2, we learned that G induces the continuous map F from the partition of X to Z, to the space Z. And then this shows us that F is bijective. So if we suppose that F is a homeomorphism, then we conclude that both F and the projection map P projection map P from X to the partition of X are quotient maps. Then this tells us that they're composite. The composite Q is also a quotient map. Then conversely, if we suppose that G is a quotient map, and then it follows from the preceding theorem, which is 22.2, that F is a quotient map. Since it's bijective, since F is bijective, F is also a homeomorphism. And then this proves part A and then part B of the corollary. Let's suppose that Z is Hausdorff. So if we have distinct points given, distinct points in the partition of X, the images under F the images under F must be distinct, and thus, if they're distinct, then they also must possess disjoint neighborhoods. We can let these neighborhoods be U and V. Then, if we have the inverse of U, and the inverse of V, then these two are disjoint neighborhoods. They're disjoint neighborhoods of the two given points from the partition of X here. So up here, this proves part A, and then this proves part B from corollary 22.3.
And now you know how a rectangle becomes a torus.
Hopefully you know more about the quotient topology now.
Yeah, like, comment, subscribe.